Hello students, this is Mr. Hatfield, and we have some information right here on the whiteboard behind me. This is information that was shared during our first day of labs here at Bullard High School in my classroom. It's the first time we've done labs in this classroom for about a year. And this is a lab called heat of solution, and we are using the same energy equation that was previously taught, which is to say Q equals mc delta T. Here, Q is the energy, M is the mass of some substance, C is the specific heat capacity of that substance, the ability of that particular substance to store heat energy, and then delta T is the change in temperature. Now, initially, when we originally introduced this equation, we tended to look at it totally from the point of view of water because it simplifies the math. You know, water has a standard for density. If you have 1 gram of liquid water, well, you have about 1 milliliter of water by volume, so it makes it real easy to directly convert measurements of volume to measurements of mass. And also, water is the typical standard for what's called specific heat, the ability to store energy. The standard for water is 1 calorie, or as we like to say in the metric system, 4.184 joules per gram degree Celsius. So initially, when we first used Q equals mc delta T, we simply focused in terms of water. It was the mass of the water, which is the same as the volume of water, times the specific heat of water, which is 4.184 joules per gram degree Celsius, times the temperature change of the water. Now, as we go into heat of solution, we're no longer talking about pure water, but we're talking about solution that is made by dissolving some substance in water. And the act of dissolving this substance could be endothermic, in which case water would be stored, rather energy would be stored in the substance and the water's temperature goes down, or it could be exothermic, where energy is released by the chemical reaction of the substance and the temperature of the water goes up. Now, in these cases, when we're talking about a solution, I want you to notice that we are also going to use 4.184 joules. But we also want to acknowledge that if we're talking about a metal or some other substance which does not necessarily react chemically with water, then we just say to be determined. Now, that could mean one of two different things. It could mean that we're going to do an activity where we do a little bit of extra math, and we don't give you the specific heat of the metal or that other substance, but we ask you to do that other math and find it. Or it could be that we are just going to provide you with that specific heat. Now, whether we're going to determine it experimentally with a little math, or we're just going to give it to you, one thing I can guarantee you absolutely, water's specific heat is 4.184 joules per gram degree Celsius, and virtually every other substance, including metals, is way less. Water is the champion. Just as water is the standard for density, 1 gram per milliliter, water is also the standard for heat capacity. Now, what does this have to do with our lab heat of solution? Well, just this. We're going to make 2 separate solutions. One of these solutions is sodium hydroxide, and the other solution is ammonium chloride. And so we have examples here of how we're handling the math. We have an amount in grams for each one. For the sodium hydroxide, it's 1.85. For this ammonium chloride, it's 10. And we have slightly different amounts of water, 20 versus 30 grams, and we have changes in temperature. One reaction is endothermic and one reaction is exothermic. That's all well and good. But notice what happens when we actually get around to doing the math based upon the problem. For the energy associated with sodium hydroxide, we're not saying 20 grams. If it was just water, we're not saying 1.85 grams as if it was just sodium hydroxide. The number we see is 21.85 grams. That's the mass of the water and the dissolved substance, sodium hydroxide, together. Similarly, for ammonium chloride, we don't say 20 grams as if it was that amount of water, or 30 grams or 10 grams. We say 40 because in this example, it's the 30 grams of the water plus 10 grams of ammonium chloride. It's the total mass. So that's a little bit of a wrinkle. That's a little bit different in that we are considering the mass of what's dissolved as well as the mass of the solvent water. But other than that, the calculations are pretty much exactly the same. You'll notice that the conversion factor is still 4.184 joules in the middle. And then we have numbers in degrees Celsius that represent the temperature change. Now notice that for the energy for sodium hydroxide, the number is positive. the temperature of the water goes up. And so at the end, the amount of joules that's calculated, that's a positive number. Whereas for the ammonium chloride underneath, well, we're going to end up multiplying it by a temperature change that is negative 7 degrees. Negative 7 degrees, it went down. Energy is sucked out of the water. It's a negative number. And so we record a negative number for the joules themselves. Now, don't let this disturb you. The fact that this number is negative doesn't mean that we're dealing with something different than regular energy. It just means that we're talking about it from a different point of view. We're talking about the point of view of the water. The water is the surroundings. And so in an exothermic reaction, the surroundings get warmer. The temperature goes up, and so the number of joules is shown as being positive, whereas in the endothermic reaction shown underneath, the surroundings of water gets colder. Energy is being sucked out of it. It's losing energy. And so the number there for joules is negative. Now, that's the perspective of the water. Is the water going up or is the water going down in temperature? That's the surroundings. But the actual reaction that did this was substances that were dissolved in water. So if we want to calculate the actual enthalpy of reaction, then we're going to use this equation. Delta H equals negative Q moles. So what is Q? Well, Q is what we calculate above when we're doing Q equals MC delta T. It's lowercase q instead of capital Q, but it's the same number, it's energy. And we're going to put that entire number in there. So for example, for sodium hydroxide, that number is positive. So the number that would go in Q is in fact positive as well. That entire positive number goes on the inside, but notice that on the outside we have a negative sign. So we're effectively going to flip the positive number in joules, and we're going to make that a negative number. And that, you might see, well, why are we doing that? Well, because now we're not interested in the energy change of what's happening to the surroundings, the water. We're asking what's happening with the substance, with the actual compound that's reacting. And so for sodium hydroxide, this is an exothermic reaction. Yes, the water gets warmer, so from the point of view of the water, the number is positive. But when we plug that number into our equation, it needs to be negative for the substance itself, because the substance is losing that heat energy. And so we slap a negative sign on it, that's the energy, and we divide it by the number of moles. How are we going to get the moles? No moles is shown in Q equals MC delta T, nor is it shown in the calculations based upon it. How are we going to get the number of moles? Well, that's real straightforward. We're simply going to take the grams of the substance being dissolved, which in this case are these numbers, right? 1.85 for sodium hydroxide, 10 for ammonium chloride. Those are the numbers. Those numbers, we're going to take the molar masses of those substances. Of course, we get the molar mass of the periodic table. We'll convert those to moles. Then we'll use the number of moles that are actually present there in the system, and we'll use that to divide the number Q, whose sign has been flipped. And for the exothermic reaction, that will end up being a negative number because the substance is losing that much energy, whereas an endothermic reaction will flip the sign. The negative will be the negative of a negative, so it becomes a positive. And for the substance in question, it'll be a positive number. Why? Because the endothermic reaction, the substance is actually gaining energy. It's storing energy. So that's the calculations we're doing based upon our data. Now, one more thing I'd like to say. The example data here I give, these are trial 2. In the actual class lab, we did trial 1. And if you were a virtual student, I actually shared individual data with you like this about what actually happened in the trials that I did with you as part of group 13. You should have actual data from the lab. But this data here is an example. It's similar data. It's very similar data you'll collect, but this would be the second trial data that you would put in the table for the handout heat of solution. And the expectation is you're going to take the actual data, which we collected in lab, either in person or virtually with me assisting you, and you're also going to take this data given on the whiteboard, you're going to combine them, you'll add them together, and then you'll divide by 2. In other words, you'll take the average of this data that was given with the actual data that was collected in the class. And that is the data that you will do the math on, where you calculate the energies of both reactions. And once you have those energies, you'll calculate the enthalpies of those reaction for those substances by dividing the negative of those energies, negative Q, by the actual number of moles that are given that we actually use, the actual number of grams of the substance converted into moles. That's what we're going to do. So I hope this detailed explanation, reminder of what was covered in class is helpful. And if you have more questions, I encourage you to come to student support between 2:15 and 3:15 most days in the course. Thank you for your attention.